All right, hey everyone. I'm gonna be going over chemquest 5. So let's get to it. All right, chemquest 5, number 1. Consider two pots of water. Each pot has the same diameter, but pot A is deeper than pot B. So there's more water in pot A. If both pots were exposed to the exact same amount of heat for 5 minutes on the stove, which pot will contain the hottest water after heating? Okay, so the way I'd approach this problem is I would first draw it out like I just like visually. So this is gonna be pot A, this is gonna be pot B. Let's say this one's like a little more elevated. There we go. It's right here, right here. A little stool right here. Okay, so it's pot A, pot B. The reason why pot B is like lifted a little bit higher is because it says in the problem pot A is deeper than pot B, so there's more water in pot A. So here's water, 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 water. So it's gonna be obviously it does show that like pot A has more water than pot B. Let's just say for example that pot A has 5 liters. Let's say pot B has 2 liters, right? So we can clearly see that like pot A has more water than pot B. Okay, so second part of the problem. If both pots are exposed to exactly the same amount of heat for 5 minutes on the stove, which pot will contain the hottest water after heating? Okay, so okay, here we go. So when heat is applied to both pot A and pot B, um, pot A will take slower to heat up than pot B. Pot B will heat up faster. This is because that pot A has a lot more water molecules than pot B, right? More volume, more molecules, there's more stuff. There's more stuff to heat up than pot B, right? So let me just refer that again. Like repeat myself, pot A just has more stuff in it. So there's more stuff, there's just more stuff to heat up than pot B. So with that being said, same can be said about the inverse. Pot B will be harder because there's less stuff to heat up. So I say pot B. Oops. Number 2. Consider question 1. Propose an explanation for the fact that even though both pots were exposed to the same amount of heat, one got hotter. Okay, so just what I just said, right? Pot B has less stuff in it. There's less water molecules than pot A, so it will heat up faster. It will heat up faster and more. So pot B, I'll say um, less volume, therefore less water molecules. Heat up. And pot A and pot A. So pot B will be hotter. Cool. Okay, fill in the blank. The greater the mass of a substance, like the water in questions 1 and 2, the blank, the temperature change when heat is applied. Okay, so greater the mass of a substance, right? Looking back at this drawing right here, which one has the greater mass of substance? Right, it's pot A. Pot A has the greater amount of substance, right? Because there's more volume in it. So when heat is applied to both A and B, and pot A will heat up slower and less because there's more stuff, right? The same thing I just said in part 1 and 2, but just the same thing happens, right? So pot A, there's more stuff in it, so there's gonna be a a lower temperature change than pot B. Just more stuff to heat up. Here we go. 4. Consider the metal hood of a car on a warm sunny day. Next to the car is a large puddle of water. The puddle of the water is so large that it has the same mass as the hood of a car. Assume that the hood of a car and the puddle are exposed to the same amount of sunlight. Which will be hotter after 2 hours, the hood of the car or the puddle? So like a different question one, I will draw it out, right? So let's say this is the hood of the car, right? It's gonna be metal. Let's say this is the puddle, right? They're the same size, same mass, same size. They're exposed to the same amount of sunlight, which will be hotter after 2 hours, the hood of the car or the puddle. So the way I approach this problem is, I think conceptually, right? Water has a large amount of heat capacity, right? Let me find it right here. Okay, here you go. Water, right? It has a larger amount of heat capacity, specific heat capacity than metal, right? This is different than oh, oops. Uh, this is different than question one because question one shows water, two water, right? They're the same like uh composition, water, H2O. The difference that number four is that um there's two different things. There's metal and there's water. So the way I answer this problem is that the metal would be hotter because water is just going to absorb all that heat. When Mr. Lee, when we do those labs, he makes us wrap the hot thing in damn piece of paper towel because the water is going to absorb all that heat. So the metal, so look at the car. Okay. Propose an explanation for the fact that even though both the hood of the car and the puddle were exposed to the same amount of heat energy and the mass were the same, one still got warmer than the other. So right, I just write down what I just said, right? So the hood will be warmer because a small amount of specific heat capacity the than water. Okay, so number six. In general, is it harder to change the temperature of metal, like on a car or hood or water? In other words, would it require more heat energy to change the temperature of metal or of water? So, right, water has a lot more heat capacity than metal, so it's going to have to take more energy to heat it up to the same temperature. So, it will take more energy to change the temp of water. Okay. One of the following, number seven, one of the following blanks you need to write 400, and another blank you need to write 200. Okay, so we're blank. If you want to change the temperature of water by 4 degrees, then blank joules of heat energy are required. But to change the temperature of metal by 4 degrees, then blank joules of heat energy are required. So right, metal, water has a larger amount of heat capacity, so it would take more energy for it to change the temperature. So the bigger number will be 400 for water, and then for metal, it's less amount of heat capacity, so it's easy to change it. So 200. Okay. Number eight, which has a higher specific heat, the water or the metal of the car, like the aluminum of the car. So, right, as you just said in question number five, right? Um, water will have a higher specific heat because water is one of those substances that just have so much like heat capacity. It's just known to it. I don't know how much else to explain it, but yeah, it's just so much heat, specific heat capacity for it. The metal of the car. So it'll be water. Instead of 200 joules heat energy applied to several objects to fill the blank. The higher the specific heat of an object, the blank the temperature change of the object. So the higher the specific heat of an object. So there's going to be two objects, right? The higher the specific heat for one object, let's say water, because water has a high amount of specific heat than the metal of a car. So water has a higher specific heat of an object. So let's just put water down here because we're looking at water. The higher the specific heat of object, the blank temperature change of the object. So this will be lower because if 200 joules, that's constant, is applied to both water and the metal of the car, the hood of the car, water will just absorb all that heat energy. So, which in turn will have a lower temperature change. Okay, so question 10, we're almost done. Given the following answers to above questions, which of the following equations is correct? So, in each of these questions, you have T equals, T equals, T equals, T equals, T equals. So in the equation is Q equals MC delta T. Basically, we know this because he said it was traumatizing because it's MCAT, right? MC delta T. So when we just isolate T by itself, we divide by MC, divide by MC. We have delta T equals Q over MC. Then we see that B is the most similar to it. So question 11. If delta T is measured in degrees Celsius, M is measured in grams, and Q is measured in joules, what are the units for specific heat capacity? So Q equals MC delta T. So T is measured in Celsius, M is measured in grams, Q is measured in joules. So when we're looking at like what are the units for, it has to cancel out. One has to equal the other. So for C, right, degrees Celsius, right? For C, it has to cancel out G and C degrees. So C will have to be G, right, keep these consistent. It'll be 1 over grams degrees Celsius equals J. And in order for J to equal J, it'll have to be J equals grams times 1 over G times C, J up here, degrees Celsius, right? We cross cancel these things out. Boom, boom. We have J equals J. That's right. And we can also see down here, right? Right here, the specific heat, the unit is J over grams degrees Celsius. That's just another way to find out. J over grams degrees Celsius. All right, number 12. What is the temperature change of a 120 gram piece of aluminum whose specific heat is 1.89 over grams degrees Celsius after 1800 joules of heat is applied? Right, so let's just look at our units. This is our mass. This is our C. This is our Q. So Q equals MC delta T. We need to find the temperature change. We need to find T. So Q is 1800, M is 120, C is 1.9, T is what we need to find. So you plug this in your calculator, you should get 4.18. No, wait, no. T degrees Celsius will be 7.9 degrees Celsius. Yeah. 13. Beer containing 250 grams of water is heated with 1500 joules of energy. If the temperature of the water is changed from 22 degrees to 23.4354, what is the specific heat of the water? So here we're trying to find C. Grams is M. Joules is Q. And here's the temperature change, right? So to find temperature change, we just subtract one by the other. Plug this in your calculator. You should get 1.435. Right. So Q equals MC delta T Q is 1500, M is 250, C is, we're trying to find what is C, and delta T is 1.435. And C will equal 4.18 joules over grams degrees Celsius. The energy is applied to 25,000 joules equal to 25,000 joules is applied to 120 gram piece brick. The specific heat is 2.45 joules over grams degrees Celsius. What is the temperature change of the brick? All right, so we need to find T. We have our Q, we have our M, and we have our C. So my pen is dying. Okay, anyways, I'll just use my finger. I'll just use my finger. So yeah, I have QC. We have Q. Hold on, give me 1 second. All right, guys, sorry about that. So we're trying to find T. So still using the same formula. Q equals MC delta T. Q is 25,000. M is 1200. C is 2.45, and delta T is what we're trying to find. So plug this all in your calculator, you should get 4.18 joules over grams degrees Celsius. The brick was initiated temperature 25 degrees. What is the final temperature of the brick? So temperature change, right, we just found out was 4.18. Oh, wait, hold on. No, wait, hold on. I did this wrong, my bad. Oh, wait, no. Hold on. No, I did this wrong. Oops. Wrong answer, guys, my bad. You should get 8.5 degrees Celsius. Get the wrong answer. It's all right. We just found the temperature change. And so 25 degrees, all we have to do is just add 8.5. Right? What's the temperature change? What's the final temperature change? We just need to add 8.5. This will be 33.5 degrees Celsius. Oops. All right. Hope that helped you guys. Catch you in the next one.